Hello, fellow students. Today, we are going to learn about vector applications, mainly about the equations of lines and planes. So the first topic we're going to talk about is lines in 2 and 3 dimensions. The first one is the vector equation for line, written as this, or if you want to expand it, you can write out as this, x, y, z components, written them in the full vector form. And r of x and y and z is this one, is any point you want to find on the line. And p of x0, y0, z0 is the non-point. This will be given to you in the question as a coordinate, and you will put them in this vector here. And v equals to abc is the direction vector of the line. So it's this thing here, after the parameter. It also represents the velocity of a particle moving on the line. And the lambda is the scalar parameter. This indicates the direction of the line, whether it is in the same direction as the velocity or different direction. The second one is the parametric equations. This basically comes from you equate each component of the vector equations. As you can see, if you just pick out the x component, the first one, s is equals to x0 plus lambda times a. So giving you this one. And the same is for the other two. And the third one is the Cartesian equation. This comes from equating the lambda in the parametric equations. As you can see, if you just move this x0 to the left hand side and divide a through, you will get lambda equals x minus x0 divided by a. And you can do the same thing for y and z, and you will get three equations linked together. The Cartesian equation is different from these two because it don't have a parameter, so it just a line itself. It doesn't have any directions in it. And in case you are not familiar with what lines in 3D looks like, I grabbed one here for you in Decimus. And the line on the right has the Cartesian equation like this. So you can see it passes the point 1, 2, 3, which is the blue dot here. 1, 2, 3 is basically these numbers here, as you can see from the previous slide. This x0, y0, and z0 is basically whatever thing is minus from the variables. And the direction vector, ABC, in this case is 2, 3, 4. It's basically what the things are in the denominators. Also from the slide previously, ABC, the denominators. And also, you can convert these Cartesian equations into parametric and vector equations. So if you remember the formula for a vector equation, this is the non-point. In this case is 1, 2, 3, given here, the blue dot. And the direction vector, ABC, in this case is 2, 3, 4, with a lambda in front. You have to write lambda is a real number at the end of this vector equation to indicate it's a scalar parameter. If you don't write this, you may lose a mark. And also the parametric equation, you can write it as well. It's very easy. Basically, you just list out each component of the vector equation separately. So 1 plus 2 lambda, 2 plus 3 lambda, and 3 plus 4 lambda. Now let's do another example, a harder one. This is from chapter 6b, 4e of the book. The question asks us to describe each of the following lines using a vector equation, parametric equations, and a Cartesian equation. The one we are going to do is a line perpendicular to the xy plane, which passes through the point 3, 2, negative 1. So, to solve this question, this point is given to us, so it obviously is a non-point. And for the direction vector, the question says the line is perpendicular to the xy plane, which means the line goes only in the z direction. So it's just going straight upward or downward. And in this case, we can pick v equals 0, 0, 1. And it does not matter if the last component is 1 or 2 or negative 1. As long as the other two components, so the x and y components are 0, you are going to be okay with it. But we usually pick with the modulus of 1 and pointing towards the positive direction. So you may recognize this. This is just a k-hat vector. We pick this simple vector to make our life easier. Following from our previous slide, we have the norm point is this one, and the direction vector is this one. So we can write down the vector equation. X, Y, Z equals the position vector of the norm point, which is 3, 2, -1 in this case, plus lambda times the direction vector. And also you need to write lambda is a real number at the end. For the parametric equations, it's easy in this case because as you can see, x is just equals to 3 plus 0 lambda. And obviously you don't need to write the 0 lambda. You just write x equals 3 and y equals 2. For z is -1 plus lambda. But notice the Cartesian equations in this case is different. It's no longer 3 equations coupled together. You only write x equals 3 and y equals 2 in this case. You don't even mention the z component. That is because for this line, you only need to restrict x to 3 and y to 2. You can see here, x is 3 and y is 2 always for this line, with no restriction on z. So you do not need to mention it as z can literally take any value. This line goes straight up and down the xy plane. Z can literally be anything. And in decimals, you will enter x minus 3 equals y minus 2 equals 0z, which just means x equals 3 and y equals 2.